Hello everyone. I want to use this video to talk about central limit theorem. And in chapter 6, we have already covered the normal distribution. And I said the normal distribution is the most important distribution because normal distribution is very common in our daily life. And after this chapter, you will find out no matter our population distribution is a normal distribution or other distribution, if our sample size is large enough for any kinds of distribution, for the sample mean, the distribution of the sample mean, the distribution of the sample sum, they all normal distribution. So in a word, so if we have a distribution which is not normal, we could use a large sample size to make sure our sample mean, our sample sum follow normal distribution. We can normalize everything. Okay, so I want to talk about the objective for this chapter. The first objective, we need to describe the sampling distribution of the sample mean or the sample sum if our samples from a normal population. And also we need to know how to describe the sampling distribution of the sample mean and the sample sum if our sample come from population distribution which is not normal. And then we need to use the central limit theorem to find the probability, like the probability bigger than something, less than something. But now we want to find the probability not for our random variable x. Okay, so for this part, we want to find the probability for the mean, the sample mean, bigger than something, less than something, or between something, between A to B. Probably for x bar less than, bigger than something, less than something, or between two values. Or we are looking for the probability for sigma x. Okay, what's the meaning of sum? Sum, that is, we add all the sample value together. The sum bigger than something, less than something, or between something. Okay, so for our previous chapters, we all focus on find the probability for x bigger than something, bigger than something, less than something, or between something. So after this chapter, we can use the central limit theorem to help us to find the probability for the sample mean and the sample sum. Okay, so I want to start with one example, which a lot of you have experienced. That is, make a cup of coffee. So I believe a lot of you have experience for making a cup of coffee. If we make a cup of coffee, if we want to check whether our coffee have enough sugar or not, what we will do? We will taste it, right? We will consider the coffee in your mouth. It tastes more or less the flavor for the coffee in the cup, right? And for that procedure, that is sampling. We are doing sampling in this simple experiment. For the coffee in your mouth, that is your sample. For the coffee in the cup, that is your population. And for the procedure, you get the coffee, you have the coffee in your mouth, that is the sampling. And you use the information in your mouth, the coffee in your mouth, to guess what happened for the population information, what happened for the coffee in the cup. For that procedure, that is inferential steps. We use sample information to estimate what happened for the whole population. Okay, so but for our daily life data, for our daily life analysis, it's not that easy. We can consider our population is very large. It's not just a cup of coffee. Maybe it's a pool of coffee. And if it's a pool of coffee, if I add sugar at this side of the pool, okay, and then I have a cup, and I grab a cup of coffee here, and then I choose another cup of coffee here, another cup of coffee here. Okay, so based on our common sense, we know if this is my first sample, this is my second sample, if this is my third sample. Okay, so maybe I choose the first sample. It's a little sweeter than the coffee in the pool, right? If I choose the second sample, maybe it's roughly the same as the coffee in the pool. And if I choose the third cup of coffee, if I choose my third sample, maybe it tastes a little bitter than the rest of the coffee in the pool, right? So if I use the sample information to estimate what happened for the population information, if I just use a cup of coffee in this scenario and then estimate what happened for the whole pool of coffee, so maybe sometimes it cannot give us that accurate information. Maybe sometimes there are some error between the true flavor with the flavor in the sample, right? So for that kind of error, we call it sampling error. So now I will give you the definition of sampling error. Sampling error is the error resulting from using a sample information to estimate the population characteristic. Like just now, I used 1 cup of coffee to estimate what happened for the whole pool of coffee. So sometimes if my sample, if I choose is very close to the place I put sugar, maybe it's sweeter than the rest. Now I believe a lot of you will have a question. So if a sampling error, that is error come from our sampling procedure, is there any chance we can get rid of sampling error? So my answer will be no. It's so hard to get rid of sampling error because our daily life is very complicated. It's very hard to choose the perfect sample. So now we will have another question. If sampling error is hard to get rid of, then how can we deal with sampling error, right? It's a kind of a rule of thumb for stats. If we have a factor which is very annoying in our analysis, and for that factor is hard to get rid of, then we will think of maybe we can reduce the effect, the influence come from that factor, right? So now I will go back to the pool of coffee example. So if we have the pool of coffee, is there any chance you can use your sample information to have a better estimation for the population information, use the coffee in your cup to better estimate the flavor for the coffee in the pool? So let's see next slide. So how to reduce the sampling error? Okay, if I use the previous example, so here are some methods I can think of. For the first method, I can think of if I have a huge mixer, I put it on the top of the pool, and then I mix the sugar with the coffee very well. Then I grab a cup of coffee in the pool, and the flavor in the cup is more or less the flavor in the pool, right? And for that, instead, we can call it minimize the potential for bias in sampling. And then this is the first method we can use to reduce the sampling error. The second method, just now we just use 1 cup, right? We can choose multiple cups. We can replicate our study. If we choose 100 cups, and then for these 100 cups, I can use that information to estimate what happened for the population information. If for that 100 cups, we have like 90 cups, they're not sweet enough, and then I decide to make more sugar. If we have 90 cups in that 100 cups coffee, 90 cups taste too sweet, and then I will think, okay, maybe I should stop putting more sugar into the pool of coffee, right? So that's the second technique we can use to reduce the sampling error. For the last one, that is the one we will focus in this chapter. We can larger our sample size. If I choose a small cup, I just take the small cup of coffee. Compare with a larger cup. If my cup is as large as the pool, then I can consider the coffee in the cup. That is a flavor for the coffee in the pool, right? So if I larger my sample size, my sampling error will be smaller and smaller, right? Now I will use one example to show you the relationship between the sample size and the sampling error. So if I have 5 basketball players, and for these 5 basketball players, I have their height. And for these 5 basketball players, this is my population. Okay, now I will choose a sample. And how to choose the sample? I will determine my sample size. For example, I choose the sample size equal to, because this example will show you the relationship between the sample size and the sampling error. So I will choose sample size equal to, sample size equals 3, and maybe I can also choose sample size equal 1, sample size equal 4, sample size equal 5. Now I will give you details for the sample size equal to. And for sample size equal to, because we have 5 basketball players, we choose 2 randomly from these 5 basketball players. So I can choose A, B, A, C, A, D, and I have 10 combinations here, right? I choose 2 items from 5. I have 10 possible combinations. And then for this column, I copy the number for the height for the basketball player. For basketball player's height, basketball player B's height, basketball player's A's height, C's height. Okay, and then I find the average. I find the average for 76 and 78. I find the average for these 2 numbers. I can get the information for this column. Okay, now I will do something like this. I have the sample information. And this is my sample information. And for my sample size equal to. Now I want to use the sample mean to help me to estimate what happened for the population mean. And for the population mean, in fact, I know it's equal the height for these 5 basketball players add together and then divided by 5. And after calculation, we can get this number is equal 80. Okay, now I want to use the sample information to estimate what happened for the population information and to visually show you the result out plot. So this is my population information. And for the sample information, because I have 10 combinations, so I will have 10 dots here. So I can find out, so if I use this sample, for the estimation, the sampling error is the distance between this dot with 80. If I use this one, the sampling error is also equal to the distance from this dot to my population information. So sometime, if my sample is good enough, the sampling error is pretty small. If my sample is not that good, my sampling error is pretty big. Now I will repeat the procedure for sample size equal 1, sample size equal 2, sample size equal 3, sample size equal 4, sample size equal 5. So there is a kind of a very clear trend. When our sample size is bigger and bigger, the variation becomes smaller and smaller. Right, the sampling error becomes smaller and smaller. If the sample size is equal to population size, the sample information is the population information. So the sampling error is kind of smaller and smaller when sample size is bigger and bigger. So sample size is bigger, our sampling error is smaller. So if I use the sample information to estimate the population information, the estimation is better and better. Right? This is our conclusion. The larger the sample size, the smaller the sampling error tends to be in estimating the population mean by the sample mean. So that gives us a clue if in the future, when we do inferential studies, if we want to estimate what happened for the population information, so it's a good idea to increase our sample size. But in the future, you will find out if our sample size is larger, we need to spend more money, spend more energy to collect the information, and also when we analyze, maybe the computation cost will be higher. So how to calculate a reasonable sample size, that is something we will cover in the later chapter. Okay. Now I will talk about what's mean of the sampling distribution of sample mean. If we have variable x and we have a given sample size, the distribution of x bar is called the sampling distribution of the sample mean. So for this part, I want to highlight this keyword. So that is a sampling distribution of the sample mean. Okay, so we need to be very, very careful about the keyword sampling. It's not a sample distribution. For the sample distribution, it's the same as a population distribution because the sample comes from the population. For the sampling distribution, that is a statistics after you do the sampling. For this chapter, we will focus on the sampling distribution of the sample mean. So that is the distribution of x bar and the sampling distribution of the sample sum. So that is summation of x. So we will talk about the distribution for these two statistics. Okay. So I want to use one example to visualize the central limit theorem, and use this. After this example, you can get the conclusion for the content for central limit theorem by yourself. Okay, so I start with a very simple example. If we have a fair die, and for the fair die we have 6 numbers, 1, 2, 3, 4, 5, 6, and we know the probability for us to have the die show number 1 is 1 over 6. The probability for the die show number 2 is 1 over 6, right? So we can get this probability. So for this part, that is our PDF, right? So if we have PDF, it's not hard for us to find the expected value. The number here multiply the probability, the number here multiply the corresponding probability, and then we add them together. So we can get the expected value. Expected value, that is the mean for our random variable. And our random variable, this is our population distribution. Our random variable is x, and we can get mean is equal 3.5. And for our standard deviation, how to calculate the standard deviation? You could have a look at the note for previous chapters. After we find the expected value, we can use every random variable value to subtract the expected value, and then we square, and then multiply the probability. And if we find the square root of this information, we can get standard deviation. If we don't use the square root, we can get variance. And after calculation, we can get this variance is equal to 2.92. Okay, so it's a very good practice. You can try it by yourself. So now we know the population information, and the standard deviation is the square root of 2.92. So we have the population mean, the population standard deviation, the population variance. In the previous slide, we know the value of x is equal 1, 2, 3, 4, 5, 6. And for these 6 numbers, that is our population. And now we will take a sample. And for sample, we can take like 1, 1. And for this part, we will use sample size equal 2. And for sample size equal 2, and we do it with a replacement. So we can take 1, 1, we can take 1, 2, we can take 1, 3, we can take 1, 4, 1, 5, 1, 6, and we can take 2, 3. So if we choose any 2 numbers from this 6 number with replacement, so that means the same number can be chosen twice, and we can get this table. And this is possible combinations for your numbers. And we will do it as before. We want to use the sample mean to estimate the population mean. And if I choose sample is 1, 1, my sample mean is 1. If I choose sample is 1, 2, my sample mean is 1.5. And I keep on doing this. Now I can, for this slide, this is a follow up to the previous slide. You can see for our previous table is here. Now I will show you what's the relationship between this table and this histogram. And for this table, we can say for our mean value, sometimes it's equal 1, sometimes it's equal 1.5. If it's equal 1, our sample, I need to have 1, 1. And because we have 6 numbers for the first die, we have 6 numbers for the second die. So the total number of combinations for our sample, we have 36 combinations. 1, 1 is 1 out of these 36 possible combinations. So that's why the probability number here is 1 out of 36. So similarly, we can have a look at other numbers. So for this bar corresponding to 1, this bar corresponding to 1.5, this bar corresponding to 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, 6. Okay, so how about we have a look at this bar? When the mean equal 5, how many combinations we have? When the mean equal 5, we can say we have 5 here. We have 5 here. We have 5 here. So we have 3 possible outcomes. So that's why the height of this bar is 3 out of 36. And you can do it for the rest of the bar. And after we get this, we can get a new probability distribution function. We can get a new PDF. And for the top, that is a value for your x bar. And for x bar, sometimes equal 1, sometimes 1.5, sometimes 2, dot, 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 until we have 5.5, we have 6. And for the probability number, we can have the probability number in the second row. That is 1 out of 36, 2 out of 36, and then 3 out of 36, dot dot dot, until we have 2 out of 36 again, and 1 out of 36. I can copy the number for the height of the bar. That is our probability value. After we have this PDF, it's not hard for us to find the expected value. So after calculation, we can find that the expected value is equal to this number. And then similarly, we can calculate the variance. The variance is equal to this number. Okay, so now we can find out something interesting happened. For the expected value for the sample mean is equal the expected value for the population. Right? So now we will have question if that works all the time. Okay, and if we compare the variance value, we will find out for this variance value, it happened to equal the half of the population variance. So now we will have question about is this always true? So how about we do for the sample size equal 5, sample size equal 10, sample size equal 25. So you can do it by yourself, try it by yourself, calculate the possible combinations for the sample, and then find the corresponding probability. Now I just gave you the result. When the sample size equal 5, sample size equal 10, sample size equal 25, after we have the histogram, I draw the histogram curve. I can find out no matter sample size equal 5, equal 10, equal 25, they all look like a bell-shaped curve. Here is our first conclusion. So for the sample mean, the sample mean is approximate to normal distribution. Okay. I can get the for this part, if we compare the mean of the sample mean, the expected value of the sample mean, I can find out no matter the sample size equal 2, equal 5, equal 10, equal 25, it all equal the population mean. Okay, so this is our second conclusion. For the mean of the sample mean is equal our population mean. Okay, you can remember this formula. So now we want to find what is the relationship between variance. For the sample size equal to in the previous example, we find out the population variance divided by 2 is equal the variance of the sample mean. Right? So if we increase the sample size to 5, to 10, to 25, we can find out it follows the same pattern. The variance of the sample mean is equal the variance of our population over the sample size. Okay, and for this conclusion, we can get the relationship between the standard deviation. If the standard deviation of the sample mean, I use this notation, is equal the standard deviation for our original population over square root of the sample size. Because the relationship between variance and the standard deviation is if I calculate square root on both sides, this is a standard deviation. Square root of the variance is equal our standard deviation. And similarly for this side, after a very simple algebra, we can simplify it's equal this. Yeah, the conclusion for our central limit theorem. So this is the content for central limit theorem. It constructed by 3 parts. For the first part, it gave you the distribution for the sample mean. The second part, it gave you the formula for the mean of the sample mean. The third part, it gave you the standard deviation of the sample mean. Okay, so now I want to highlight this part. For the first sentence, the distribution of the means will approximately to a normal distribution for a large sample size. Okay, the approximation becomes more accurate as n becomes larger. So for this part, we will have a question: what's the mean of a large sample size? Is n equal 10 large enough? Is 10 equal 100 large enough? What's the mean of large? Okay, in the following slide, I will show you what's the mean of large. And for the second part for central limit theorem, you need to remember this formula: the mean of the sample mean. So for the left side, it represents the mean of the sample mean is equal the population mean. Okay, so for this notation, this is the mean of the sample mean. And for this one, this is the mean for the population. They always equal, no matter the sample size. Okay, and for the third sentence, the standard deviation. This notation represents standard deviation of the sample mean equal the standard deviation for the population over square root of the sample size. And for this part, we can say for our standard deviation, it will become smaller and smaller. So that means the variance, the spread for our data, it will become smaller and smaller if our sample size become bigger and bigger. So that explains the previous conclusion. If our sample size is increasing, our sampling error is smaller because our standard deviation of X bar is smaller. The standard error equals the standard deviation of the population divided by square root of the sample size. So you can just remember this formula to help you. Okay, we have a look at this example. This example just practice the formula for the mean and the standard deviation. If we have a sample size equal 25, determine the mean and the standard deviation of X bar. The mean of X bar we know is equal to the population mean. The population mean 72. The standard deviation of X bar is equal to standard deviation of the population over square root of sample size. Standard deviation of the population is equal to 5. Square root of sample size, square root of 25. So that is 5, right? 5 over 5 is equal 1. 5 over 5 is equal 1. The practice for the formulas, now I want to explain what's the mean of the sample size is large enough. Okay, so we do some empirical study. If our population distribution is normal, we can say if our sample size equal 5, it is still bell-shaped curve. Sample size equal 10, bell-shaped curve. Sample size equal 30, bell-shaped curve. But we can say when our sample size is bigger and bigger, our bell-shaped curve, it becomes narrower and taller because the standard deviation is smaller. Because we have the standard deviation of sample mean is equal to standard deviation over square root of n. And for this part, the standard deviation is sigma. And for this part, the standard deviation is sigma over square root of 5. For this part, the standard deviation is sigma over square root of 10. This part, the standard deviation sigma over square root of 30. So sample size is bigger and bigger. The standard deviation is smaller and smaller. So that's why our bell-shaped curve is narrower and narrower. Okay, so for this bell-shaped curves, we can get a conclusion. If our population distribution is a normal distribution, then no matter your sample size is 1, 2, 3, we don't care about the sample size. It's always a normal distribution. Okay, and now we will have a look at this two graph. Okay, and for one graph, the population distribution is a uniform distribution. Another one is a skewed distribution. And for this one, it is skewed to the right. Okay, this one is skewed to the right. So if it is symmetric, we can say the sample size equal 5, the sample size equal 10, the sample size equal 30. So they all look like a bell-shaped curve. If it's skewed, for this one, it's still skewed to the right. This one is still a little skewed to the right. Until our sample size is equal 30, it looks roughly like a bell-shaped curve. So if we compare these two, okay, we can get a conclusion. If our population distribution, is not normal, if our sample size is larger than or equal to 30, we can get the distribution of the sample mean is approximate to normal distribution. Okay, so now I will give you the conclusion regarding when our sample size is large enough to apply central limit theorem. Okay, and here is a conclusion. You can read this part by yourself, and also you can use my tree diagram to help you to remember this conclusion. Okay, so when you get a question in this chapter, always asking yourself, what is your population distribution? Okay, if your population distribution, for your population distribution, you have two scenarios. Sometimes it's normal. sometimes it's not normal. If it's normal, that's great. We don't need to worry about the sample size. For our X bar, it's a normal distribution. And then we can find the probability for X bar bigger than something, less than something, between something with a normal CDF. If our population distribution is not normal, okay, for this part we need to be very, very careful. Only if our sample size at least 30, so that means n bigger than or equal to 30 for our X bar is approximate to normal. Approximate to normal. So that means we can use the normal distribution to help us to figure out X bar bigger than something, less than something, between something. We have requirement for our sample size. So 30 is a kind of benchmark. So if it's bigger than or equal to 30, okay, it's big enough. The sample size is big enough to apply central limit theorem to solve the problem. If sample size, if we are not that lucky, we don't have enough sample. If our sample size is less than 30, okay, so I will use another color to divide to two parts. Okay, for this part is normal, and for this part is not normal. If our sample size is less than 30, okay, if I'm looking for the probability for X bar bigger than something, less than something, or between something, I don't have enough information. So my answer will be I don't have a solution, or I don't have enough information, or it need to be determined by other information. Okay, so we don't have a solution. So if we have this scenario, X bar is normal, or X bar is approximate to normal. So no matter we have this or this, we can use our calculator function, normal CDF, to help us to find the probability. We can use our inverse norm to figure out the random variable value, X bar, like finding the percentile. Okay, so I will show you this. This is important to remember. Okay, so every time once you get a question in this chapter, follow this tree diagram. Use this flow chart to help you. Okay, so asking yourself, is this population distribution normal or not normal? If it's normal, go to this pathway. If it's not normal, go to this pathway. And then asking yourself, what is the sample size? If it's bigger than or equal to 30, go through this way. If it's less than 30, go through this way. Okay. So now we can try this example together. For this example, let's have a look at, we've just followed the flow chart. So our flow chart, the first information we need to know is the population distribution. So the population distribution, we can say here we have a keyword. The distribution of the incomes is skewed to the right. So if it's skewed to the right, that means it's not normal. Right? It's not normal. If it's normal, it should be symmetric. So it is skewed to the right, that means it's not normal. If it's not normal, we need to have a look at the sample size. For this question, the sample size equals 60. Sample size equals 60, so X bar approximate to normal distribution. So we will choose A. X bar approximate to normal. Now have a look at this question. So for this question, we have a keyword here. This is unknown distribution. Okay, it's unknown, so that means we cannot guarantee it is normal. So we do care about the sample size. And we have two questions. These two questions, they are very similar. And for A, the sample size is equal 50. For B, the sample size is equal 15. Okay, so for A, the sample size is large enough. So for A, X bar is approximate to normal distribution, with mean equal population mean with standard deviation equal population standard deviation over square root of sample size. And the mean is equal 0.5, so that is 0.5. The standard deviation is 0.289, that is population standard deviation over square root of the sample size. So this is distribution for X bar. For B, we don't have enough information because our sample size is too small. So for B, no solution. Right? So for this question, it's asking us which one we can apply central limit theorem, the first one. And if I add one more question, if you know the first one can apply central limit theorem, how to find the probability the mean is below 0.3? How to find this probability? We need to use some knowledge we covered in chapter 6 in the normal distribution part. We know x bar follow normal distribution. We want to find the probability for x bar below 0.3, less than something. We are looking for probability, and for our random variable follow normal distribution. So we need to use a normal CDF. And for normal CDF, we need to input 4 numbers. Minimum value, we don't have minimum, so we use negative 10 to 99 as our minimum. We don't have lower bound, right? And for our upper bound is 0.3. For our mean is 0.5. For our standard deviation, I just copy this number and put it here. Input this into calculator, it will give you the probability. Example 4. The average age of a vehicle registered at United States is 8 years. 8 years, that means 96 months. Assume the standard deviation is equal 16 months. And if a random sample of 36 vehicles is selected, find the probability the mean of their age is between 90 and 100 months. Okay, so for this question, we can say we are looking for the mean of their age is between 90 and 100 months. So if we translate this into mathematics language, it's equivalent to find the probability for the mean between 90 to 100 months. Okay, and for this question, we don't know anything about the distribution of x, but we know the mean of x is equal 8 years, that is 96 months, and the standard deviation is 16 months. So that's the only information we know for the population. So we know the population distribution we cannot guarantee the population distribution is normal. Then we need to have a look at our sample size. Only if our sample size is large enough, I can find the probability. For this one, the sample size is equal 36, so it's large enough to apply central limit theorem. So we can apply to central limit theorem x bar approximate to normal distribution. So I can use a normal CDF. And then I need to input 4 numbers. Minimum 90, maximum 100. For the mean is equal 96. For the standard deviation is equal 16 months over square root of the sample size. So input this to calculator, you will find the probability value. Example 5. For example 5, the first sentence, it gives us the population distribution is normal. So that's great. We don't need to worry about the sample size, right? And we know the mean, we know the standard deviation. And for A is a little tricky. We are looking for if a student is randomly selected, what is the probability for this one student verbal score is above 500. So we only have one student, and for this student is selected from our population. So for this distribution, for the verbal score for this student, it follow our population distribution. And for our population distribution is a normal distribution with mean equals 430, with the standard deviation is equal 120. And for A, we are looking for the probability for only one student. One student, we don't need to find the mean for this one student because the mean for this one student is still equal the original score for this one student, right? So for this one student, verbal score above 500. So it's a normal CDF. Minimum 500. Maximum, we don't have upper bound, so we use 10 to 99 as our upper bound. For the mean, that is our population mean. For the standard deviation, our population standard deviation. And for B, for this question, we have a sample of 35 students. What is the probability for the sample mean will about 500. So we transform to mathematics language. What is the probability for the sample mean? About 500. So we are looking for this probability. And the probability for sample mean about 500. And our sample size is equal 35. Our sample size is equal 35, so I will write sample size here. Sample size equal 35. Because our population distribution is normal, so the sample size bigger than 30 or less than 30, we can always solve the problem, right? And this one, we can use a normal CDF. The minimum is 500, maximum 10 to 99. And for the mean is equal 430. For the standard deviation is equal population standard deviation over square root of the sample size. So input this into calculator, you will find out the probability is equal very, very small number is roughly 0. Okay.